introducing me. So welcome. So my name is Sybren Jansen, Head of AI and Machine Learning Engineer at Slimmer AI. And so just a few words about Slimmer AI. So we are an AI business-to-business venture studio, and we're both based in Groningen and Amsterdam. So what we do is we collaborate with industry to continually advance our AI capabilities. We build new ventures together with promising founders, and we invest in business-to-business ventures where we think can disrupt industry through applied AI. So today, and this might shock you, as a machine learning engineer, we apply machine learning. And those models, when you train them, they're often data hungry. You need to feed them a lot of data. So for this to work, you need to have fast data processing. You don't want to wait forever. You don't want you continually want to utilize your GPU. So fast data processing is needed to analyze, clean your data up, etc. And Python is a great choice for this because of the fantastic open source community that brought us scikit-learn, but also PyTorch, TensorFlow, and all the pre-trained models that come with it. However, even though the development speed is really great in Python, the execution speed, as you might know, is a whole other story. And there are workarounds available, and one of them is writing your performance-critical code in Python, C, C++, and they have actually done this with libraries you might know, like NumPy and SciPy, which actually make Python really useful. However, if you're just starting or you're a little bit more advanced, but many programmers don't know these other languages, and that's not why you chose to use Python. It can be really time-consuming to rewrite everything in a different language, and it's definitely not ideal for experimentation settings. You might just want to optimize a single thing, and then using and rewriting it in Python. Well, it's not ideal when you can only use it once. So what else can you do? Well, most of the time you have a laptop or a machine where you have multiple cores, and if you're using vanilla Python, you're only utilizing a single one. So why not use multithreading? And so this is the ability of a CPU to provide multiple threads of execution concurrently, which sounds great. The advantages are that every thread can access the same shared memory. So whenever a thread changes anything, the other threads notice it. However, and we had this talk this morning about the GIL, there is the infamous global interpreter lock. And this basically prevents you from executing threads concurrently whenever you want to access Python objects. So you can still write your code in C or Python where you can release the GIL, or maybe you're working on IO-bound tasks and then multithreading can work fine. But for most tasks, you need to resort to something else. And that something else can be multiprocessing. So instead of creating multiple threads, you actually spawn multiple Python processes. So each Python process has its own GIL, and therefore the GIL is no longer a concern. The major disadvantage, however, is that there's no shared memory. So whenever your Python process makes a change, the other Python processes don't notice it. So every time you want to submit tasks or you want to get back results, you have to communicate through pipes or queues and serialize all your objects, and that causes a lot of overhead. But it'll have to do. So I wanted to go a little bit so I mentioned in the previous slide, Python processes can be forked or spawned. Fork means that each child process inherits all the variables and more from the parent. So, and from then on, each child is independent. Fork is available on Unix systems, but unfortunately not on Windows. And there you have spawn, where Python starts fresh new Python interpreters. So every time you need to you start a process, then all modules have to be re-imported and variables recreated. This can be useful in its own right, but usually fork is faster and can be exploited in some ways. I'll get back to that later. So MPIRE is a multiprocessing library, and you might be thinking, well, there are plenty out there already. Well, yes, definitely. You have the multiprocessing module and process pool executor, which are available in a Python standard library. And then you have your third-party libraries like joblib, Dask, and Ray. And the latter two are actually also distributed computing platforms if you want to distribute your work over multiple machines. However, when I started building MPIRE 4 years ago, none of them were working to my satisfaction. Either they had missing features, introduced a completely new syntax where you're just used to vanilla multiprocessing, They had very poor error handling, and for the case of Dask and Ray, well, multiprocessing on a single machine was often sufficient, and then setting up a whole cluster of workers can be quite a nuisance. I'll get back to showing you several examples of these during my presentation. So to give you an example of why I decided to start MPIRE, to build MPIRE, so this is a function called matchSample. It receives a sample string, and this string can contain information like the city, country, organization name, and we want to match that to a database of organizations. So in this case, we want to then do some cleaning up, normalization, and match it and return the organization ID. So in the future slides, I'll just skip all the typing imports and just stick with a function definition. And so if you want to do this just with single processing, you load in your organization database, your data set, and you loop through the data set and call matchSample for each sample, and you store the organization IDs. Sounds pretty simple. However, in my case, I had millions of samples. The database of organization contained a few 100,000 samples, so running this on a single CPU took forever. So let's solve this with multiprocessing. So in this case, we import multiprocessing.pool, and the only thing that we add is we say with pool 20 workers, and then we call pool.map on that function and data set. And because I need to pass in the organization database every time and again, I wrap it in a partial function, which makes it a little bit nicer. But pool.map calls the match function on each sample in the database and returns the list of organization IDs. Sounds pretty simple. However, the database is being copied for every task. And I already mentioned we have millions of samples, so a database maybe of a few hundred megabytes is copied a million times. You definitely don't want to do that. The runtime actually was slower than on a single CPU. So what are some alternative options? Well, first off, you could use global variables. They are considered bad practice, and you should definitely not be using them, except when you're defining constants, or maybe you're in a Jupyter notebook and you're experimenting, then sure, go ahead. But other than that, don't use it. You could wrap the database using a multiprocessing.manager. So what this means is that the database lives in a separate process, and every time you want to get something from the database, then you need to communicate through it using pipes or queues, and again, that's slow, especially if you have to do that a million times. In Dask and Ray, you have the option to use broadcast or scatter. So in that case, the database is copied to each worker only once. So that's already better than copying it a million times for each task. But again, you're making copies, and if your database or whatever object you're trying to share is a few gigabytes, and you want to have 40 workers, then you can quickly run out of memory. So in my case, this was also not an option. Then you could use an actual database. Well, that sounds like a lot of work. And it's also besides the point, because, well, maybe in this example you want to share a database, and maybe in another example you want to share something completely different, and then a database is not appropriate. So what can you do? So you could ditch the whole idea of using multiprocessing.pool. And the nice thing about using a pool of workers is that it takes care of all the inter-process communication for you. But you could use process, which gives you a little bit more fine-grained control. And the nice thing about it is that when you're using fork as a means of starting your processes, then whatever you pass to the constructor of a process, those objects are being passed as copy on write. And what I mean with that is that so as long as you don't make any changes to the Python object, all workers share the same memory address for that object. Only once a worker makes a change, then for that worker the object is copied. In my example, I only read from the database, so that's all good. We're fine. So, and again, if you're a Windows user, I'm really sorry, this won't apply to you. But MPIRE does feature other features that might still be useful for you. So, are the downsides? Yeah, definitely. You have to do all the inter-process communication yourself, and that boils down to a lot of boilerplate code. I'll just give you a quick example. Don't try to understand everything what's going on here, but this is just to show you how much code you need to write every time you want to do this. And this is actually the foundation of MPIRE. MPIRE is has the same interface as a multiprocessing.pool, but with the additional shared object capabilities of a multiprocessing process. So how would it look like when you do this with MPIRE? So here's the example again with multiprocessing the pool. And for MPIRE, you of course have to change the import. But other than that, you say instead of with pool, you say with worker pool. And we want to share the organization database, so we say shared objects is organization database, and then the rest is pretty much the same. So how about speed? What does it actually translate to? Well, in my example, the above took about 7 hours to run, around 22.3 gigabytes of memory. And in MPIRE case, it was done in less than 5 minutes, and it doesn't even take more than a gigabyte of memory. That's a pretty huge win. We benchmarked a similar task for all the multiprocessing libraries that I mentioned earlier, and we can actually see that, well, multiprocessing and the process pool executor are slower, but Ray, Joplib, Dask, and MPIRE all are pretty fast, much faster than the others. So we're good on that front. So what else? Is that all? No, definitely not. This is where MPIRE started, but during the years we added many more features. And one of them is user-friendly exception handling. So suppose you have a function which multiplies two numbers, divides it by a third number. And you can imagine that if you divide by 0, then of course you get a 0 division error. When executing this piece of code on a list of data samples, we see indeed in Ray it gives back a 0 division error, but that's pretty much it. So suppose you're executing this piece of code on millions of data samples, and after a few hours of running, it suddenly crashes, and you still don't know what actually caused the error. You only know that it's this function and it's a 0 division error. You don't know what the input arguments were, nothing. So in MPIRE, you see that it's an error in line 3, and you actually see what the line is. And on top of that, you see that on the top, you see that the 3 arguments that were passed to that function. And you can verify that indeed the third argument was 0. The only other library to do that is Dask, but I was surprised to see that none of the other libraries offered this. So what else? So every time I write a piece of code that runs for more than a few minutes, I always want to know how long it will take to finish running. So I add a progress bar almost everywhere. And I was surprised to see that almost no multiprocessing library out there offered this out of the box. So MPIRE, with MPIRE, we utilized the TQDM progress bar library, and we also added a small Flask dashboard, which provides a little bit more information. So when we go back to the earlier examples of matching a sample to the database, this is the same implementation with multiprocessing without the progress bar. And if you want to add a progress bar, you have to, first of all, go from pool.map to a pool.imap, so which is the lazy version of map, which returns objects as soon as they're done. And additionally, you have to wrap it in TQDM and make it a list comprehension and so on. So there's a lot of changes that you need to make to get this working. And in Ray, you have to add a lot more boilerplate code to get a simple thing as a progress bar working. So in MPIRE, so this is the same line of code you saw earlier, but with progress bar, we only have to add progress bar is true, and then you're pretty much done. It shows a nice TQDM progress bar on terminal, and also if you're using a Python notebook, it switches to the widget automatically. And if you've started the MPIRE dashboard, it will automatically register to the dashboard as well. Then, so almost every multiprocessing library offers some kind of worker initialization. So whenever a worker is started, an initialization function is called to maybe set up something. But I noticed that when you want to, for example, load a machine learning model, or you want to set up a database connection and store something, then you can't really do that. So except if you were to use global variables, which I definitely don't recommend. So in MPIRE, we added something called a worker state. So each worker has its own state, and this is passed to the worker initialization function, as well as the task that you're actually executing. And so you can store in it whatever you want. And we also added an exit function, so if whatever you need to clean up, you can do that there. And you can actually also return something from the exit function whenever a worker is finished working. And I'll give you an example of that in a short while. First, I wanted to show a different example. This is actually a second benchmark where the task was to load a machine learning model and predict on a stream of incoming data. And even though the model took only a few seconds to load, if you have to do this millions of times, then it's going to slow it down your code dramatically. So this is the example when you're just using multiprocessing.pool. So we have the evaluate next batch function, which takes a model file name and your data, loads the model every time again, returns the results. This takes forever to run. In MPIRE, we specify a worker init function, which also receives the model file name and also the worker state in this case, and we store the model that we load in a worker state. So this is only done when a worker is started. And then we have the evaluate next batch, which now also receives the worker state, and you can directly use the model from there. So the only changes that we needed to make is say use worker state is true, and then a worker state is passed to every function that's being called, and we have to say worker init is the worker init function, and you're done. So when we benchmark this task for all the multiprocessing libraries, you can clearly see that MPIRE and Ray and Dask as well are beating the competition. Dask doesn't really have native support for storing state, so I had to hack my way around it. And as you can clearly see, when you add more workers, then this starts to fail. So it doesn't scale that well. So the other example of the exit function, this is actually the third benchmark. So in this case, we had a small task where we wanted to count the number of unique words across an entire data set of documents. So we could, and the naive way would be to return the counts after each document has been processed, but then you would, because a lot of documents have overlap in the words, you would return a big dictionary every time and again and again. What if we could store the counters on each worker and only return after we've processed all documents? That would save us a lot of communication overhead. And that's what MPIRE offers. So when we benchmark this task, we can even see a more dramatic effect where MPIRE and Ray definitely beat the rest. And the funny thing is that multiprocessing here in this case is actually slower than just using a simple CPU. And that's because if you want to do this with a shared state, then you need to resort to using a multiprocessing.manager, and like I mentioned, that has a lot of communication overhead. But MPIRE and Ray scale really well. So, of course, there are more functions, even of features, even more than they are mentioned here. Just wanted to go through them quickly. So we have worker insights. So this gives you more insight in your multiprocessing pipeline. So it won't profile your function, but it will measure like the amount of working time, the amount of time it's sitting idle and waiting for tasks, and so on. So this really gives you the ability to optimize, for example, your chunking or whatever. Then there's CPU pinning. You can pin your processes to specific CPUs or a range of CPUs if you so desire. And the last one that I wanted to mention is that by default, multiprocessing uses Pickle as a serialization backend as a way to send over data. But Pickle has its downsides. It can, for example, it's unable to pickle Lambda functions, and maybe some objects are not pickleable. And in those cases, you can utilize DIL as a serialization backend. So this is optional. And this is also, for example, useful in Jupyter notebooks or and so on. All right, so if we combine all the benchmarks, so we normalize them and we add them together, then Ray and MPIRE clearly are the fastest overall. So in summary, so if you definitely need distributed computing, then go for Ray. I would say it's a fantastic library. It's pretty fast. However, you do need to, if you want to share an object, you do need to make copies for each worker, which might be a huge downside. But if a single machine is sufficient, and in my experience, a single machine often is, as long as you optimize your code well enough, which you can do with MPIRE, then definitely use MPIRE. MPIRE is really easy to learn. The syntax is almost the same as using multiprocessing. Has many features, user-friendly exception handling, and as you saw, it's consistently faster than the other competitors out there. just wanted to quickly share with you the impact of MPIRE so far. So we released this package a few weeks ago on GitHub. We also shared on it on Reddit and LinkedIn and Medium. We got some fantastic comments and responses. And it's been featured on a few websites already and podcasts like Python Bytes. Really nice to see. So if you want to learn more about MPIRE, then definitely check out our GitHub page, documentation. There's a blog post that gives a little bit more detail about the benchmarks that I just showed you and a few more examples of how to use it. And if you want to learn more about Slimmer, you can find us at slimmer.ai and definitely follow us on LinkedIn. Thank you.
Thanks, Sybren. We have time for questions, yes.
I wonder, does PQDM have any performance penalties on your execution?
Yeah, so I'll repeat the question indeed. So the question was if TQDM has any performance penalty if you use it. They are negligible, so it's just nanoseconds. It's not really noticeable.
Any other questions? We have plenty of time, so yeah.
That looks very good, but what kind of projects have you used this with?
So at Slimmer, so we've used this for data cleaning pipelines, normalization. There's also one of our ventures that uses it to just process large amounts of data to get it just quickly and done. And yeah.
So I'm guessing all of the benchmarks have been done on Linux machines.
Yeah.
How does it compare on Windows machines? The performance is great, but
Yeah. Yeah, no, definitely. I have to admit that Linux and macOS are the target audiences, but due to popular demand, I made it available in Windows as well. However, as I mentioned, Windows doesn't have fork, so the shared object capabilities won't work. But you can still benefit from the shared of the worker state, the worker init and action function, and so on, and the built-in progress bar that still works. And if you just stick with that, then the performance is comparable to on Linux.
Thanks, very nice talk. Do you think it would be in some way possible to integrate it into Airflow?
So the question is, can we integrate it in Airflow? So I know that Airflow is like a pipeline. Yeah, definitely. I mean, one of our ETL pipelines runs in Airflow, and we have individual parts that utilize MPIRE. But other than that, I'm not an expert in Airflow, so I can't tell you more about that. But we have colleagues here that are experts in Airflow, so I think we can afterwards discuss that further.
Want to see in the back any other questions also over there? So I guess we're a little bit early then, so I want to thank the speaker again.